Welcome, my friends. In this video, we will discuss two special right triangles, which are the 30, 60, 90 degree triangle and the 45, 45, 90 degree triangle. Let's begin with the 45, 45, 90 degree triangle, which looks like this. Since two of the angles are equal, the side lengths opposite to those angles will be equal as well. The sides opposite to the 45 degree angles are the two legs. Since they are both equal in length, we can label them both as x. Since we have a triangle that has two sides that are each equal to each other, this is what we call an isosceles triangle. If we want to find the length of the hypotenuse, we can use the Pythagorean theorem. The two legs, a and b, are both x, and the hypotenuse is c. We have x squared plus x squared is equal to c squared. Combining the left-hand side, we have 2x squared is equal to c squared. Now, remember, we are solving for the length of the hypotenuse c, not x. So at this stage, we can take the positive square root of both sides. The negative square root wouldn't make a lot of sense since we are dealing with side lengths here. The square root of x squared is just x, and we can't do any further simplification with the square root of 2. On the right-hand side, we are left with just c. Altogether, we have that the length of the hypotenuse c is equal to the length of either of the legs times the square root of 2. Here's the general way that you will see a 45, 45, 90 degree triangle written, with each leg as x and the hypotenuse as x times the square root of 2. If we wanted to describe this finding in words, we might state that, in general, for any 45, 45, 90 degree triangle, the length of the two legs will be equal, and the hypotenuse will be the square root of 2 times the length of either leg. Let's look at a few examples of using this idea to solve for the missing side lengths of a triangle. I have the general 45, 45, 90 degree triangle in the bottom right-hand corner of the screen to help us if we need it. Here we have a 45, 45, 90 degree triangle, where one of the legs is 4 units, and we would like to find the length of the other two sides. We are told that one of the legs is equal to 4, so that means that x must be equal to 4. If one of the legs is equal to 4, we know that the other leg must also be equal to 4, because the two legs will always be equal in a 45, 45, 90 degree triangle. The hypotenuse could be solved by using the Pythagorean theorem, but the point of recognizing special right triangles is to save you time, and if you remember that the hypotenuse is just the length of one of the legs times the square root of 2, there's no need to use the Pythagorean theorem. Let's label the missing hypotenuse as c. The hypotenuse of a 45, 45, 90 degree triangle is the length of one of the legs, x, times the square root of 2. Since the length of each leg is 4, the missing hypotenuse length must be 4 times the square root of 2. You could type this into your calculator to get a decimal approximation, but 4 square root of 2 is the exact answer, and is oftentimes preferable to a decimal approximation. Let's try another one. This one is a bit trickier because we already know the hypotenuse and need to solve for the two legs. As this is a 45, 45, 90 degree triangle, the length of each of the legs should be the same, so let's label them both as x. We also know that the length of the hypotenuse must be x times the square root of 2, so let's set up an equation. The hypotenuse of 6 must be equal to x times the square root of 2. If we divide both sides by the square root of 2, we get that x is equal to 6 over the square root of 2. It's improper to leave a square root in the denominator, so let's rationalize the denominator by multiplying by the square root of 2 over itself. This won't change the answer, as we are simply multiplying by 1. The square root of 2 over itself is just 1, but it will change the way that our answer looks. We have 6 times the square root of 2 divided by 2, since the square root of 2 times itself is 2. 6 over 2 is equal to 3, so we have 3 times the square root of 2 as our answer. Both of the missing side lengths are 3 times the square root of 2, and we can update our picture to include the values of the side lengths that we solved for. Let's discuss the other special right triangle, which is the 30, 60, 90 degree triangle. Deriving the side lengths for this one is a little bit trickier than the 45, 45, 90 degree triangle, and we actually start with an equilateral triangle, which has 60 degrees for all three angles. Note that if all of the angles are equal in a triangle, all of the side lengths are also equal. let's label each of these side lengths as 2x. The reason we label these sides as 2x is because the next step is to split the triangle in half, right down the middle. This will create two smaller right triangles. These two angles are still 60 degrees, but the top angle has now been split in half, so that each of these smaller triangles now have a 30-degree angle. Let's just consider the leftmost triangle, which I have copied over here to the right. We know the length of the hypotenuse is 2x, as that came from one of the original sides of the equilateral triangle. We also know that the base is x, because that came from splitting the triangle in half, which in turn halved the base. What we are missing is the second leg, which we can solve for using the Pythagorean theorem. The first leg of a is x. The second leg is unknown, so let's call it b. The hypotenuse of c is equal to 2x. Plugging into the Pythagorean theorem, we have x squared plus b squared is 2x squared. Make sure that you have 2x in parentheses, because that entire term needs to be squared. Squaring the right-hand side, we have x squared plus b squared is equal to 4x squared. If we subtract x squared from both sides, we get b squared is equal to 3x squared. Remember that we are solving for b, so the next step is to take the positive square root of both sides. We get b is equal to x times the square root of 3, as the square root of x squared is just x. Here is the general form of how you will see the sides labeled on a 30, 60, 90 degree triangle. In general, for any 30, 60, 90 degree triangle, the length of the hypotenuse will be twice the length of the smaller leg, and the length of the longer leg will be the length of the shorter leg times the square root of 3. Let's take a look at some examples. Just like before, I have the generic special right triangle in the bottom right corner for reference. We want to solve for the missing leg as well as the hypotenuse. We already know the length of the shorter leg is 5, which in general we label as x. Let's label the missing leg as b and the hypotenuse as c. The hypotenuse is easy to solve for because it's simply 2 times the shorter leg, so the hypotenuse of c is 2 times 5, which is equal to 10. The longer leg b is x times the square root of 3, which is 5 times the square root of 3. There is no simplification necessary. We have our final answer and can place the missing side lengths onto the triangle. How about this one? This time we know the hypotenuse is 6, and we need to find both of the legs. The most obvious thing to do in this situation is halve the hypotenuse, and then you will have the shorter leg length. Half of 6 is 3, so the shorter leg length must be 3. Now we can remember that the longer leg is just the shorter leg times the square root of 3. The shorter leg of 3 is equal to x. If I let the longer leg equal b, I have that b is equal to 3 times the square root of 3. We can update our triangle with the side length of b, which we have found. Let's try one final problem. We already have the longer leg this time, opposite the 60-degree angle. This side in general is x times the square root of 3, where x is the length of the shorter side. We also know that the hypotenuse is twice as large as the shorter leg x. Let's label the shorter leg as x and the hypotenuse as c. Let's solve for the shorter leg x by setting 4 equal to x times the square root of 3. Dividing both sides by the square root of 3, we have that x is equal to 4 over the square root of 3. Rationalizing the denominator by multiplying by the square root of 3 over itself, we have that the length of the shorter leg is equal to 4 times the square root of 3 over 3. That means that the hypotenuse of c must be twice as large. If we multiply our result by 2, we get 8 times the square root of 3 over 3 as the length of the hypotenuse. We can update our triangle by putting the side lengths that we found onto the sides of the triangle. Alright my friends, that wraps up my video discussing special right triangles.